So we've got the equation of motion, or the equation of state, that d rho dt plus dq dx must equal 0. And we also know that q is equal to the velocity times density. So those are all true. They have to be true unless you've got some slightly weird thing happening, like cars disappearing or driving off the road. But now we need a relationship, and we know that the velocity is a function of density. But we need to know what that's equal to. Okay, just before we do that, we're going to substitute in here. So we've got d rho dt plus d by dx of v of rho times rho equals 0. And then we go, that's going to be d rho dt plus, and I'm going to differentiate that, I'm going to get v dashed of rho times rho times d rho dx. When I differentiate this, I'm going to take the x inside and get d rho dx. This rho comes from here, plus I'm going to get v of rho times d rho dx equals 0. So the equation becomes d rho dt plus v dashed of rho times rho plus v of rho times d rho dx equals 0. And that there we call c of rho. So c of rho is equal to v dashed of rho times rho plus v of rho. Okay, brilliant. And the equation of motion can be written over here as, in another form, as d rho dt plus c of rho, and this is the sort of standard way we'll write it, d rho dx equals 0. So this is the equation. Of course, this thing here, still we don't know what the c that depends on rho is, because it depends how the velocity depends on rho. So that's the next thing we're going to work out. So how does the velocity depend on the function of rho? What does that equal? And we make some pretty simple assumptions. We assume that when the density is equal to 0, the velocity is equal to v naught, so which is the speed limit, or whatever you want to say. Okay? And when the velocity is equal to rho max, which is bumper-to-bumper traffic, the velocity is equal to 0. So here's our graph. Here's rho max, and here's v naught. And we have a straight line between them, which I'm going to try and draw. So we're going to have the velocity is equal to rho max minus rho multiplied by the slope. Okay, making sure because the slope's positive, which is v naught over rho max. Okay, tick. No problem. So that's the velocity. And then we're going to draw onto this graph a couple of other quantities of interest. The first one is q, which is equal to rho times v. So that's going to be equal to v naught over rho max, rho times rho max minus rho. So if I draw that on this curve, we get a curve that comes up and looks like that. That's what Q looks like. And it has a maximum here at rho max over 2. And it's interesting, so the maximum flux here is Q is maximum when the speed is, the velocity is equal to v naught over 2. Which is interesting, so that the maximum flow of traffic is when the traffic's moving at half the speed limit, which is kind of interesting. And it's common on toll roads in Sydney to be moving at that speed. So good to know the toll company is making maximum profit. And then finally, we've got C. So C is equal to, what did I say it was? V dash times rho plus V. So it's the derivative of that is going to be minus V naught over rho max. So it's V naught rho over rho max with a minus plus V, which is V naught rho max minus into rho max minus rho. So that simplifies to become V naught over rho max minus 2 rho. So the velocity, the blue is Q, C, the purple curve is that. Comes down, straight line here, and comes down to be 0. So this is the curve for C. Comes down here as a minus V naught. Okay, we don't quite know what C is, but C is the speed of the disturbances in the traffic. And it's a very important quantity we'll see shortly, but it's positive if the velocity, so the disturbances in the traffic, if there's a light density of traffic, disturbances will flow forward, and if there's a high density of traffic, they'll flow back. So which is why you get jams forming in high density of traffic, because they start propagating back, and we'll see that causes all kinds of problems. Okay, I'm going to finish there.